time dilation via speed. So, you want to travel in time? Forget the DeLorean, forget the swirling vortices and the temporal paradoxes that give philosophers headaches. The first and most realistic entry on our list doesn't require a flux capacitor. It just requires you to go mind-bogglingly, absurdly fast. Welcome to the strange world of special relativity, Albert Einstein's 1905 mic drop on the nature of reality. The core idea is deceptively simple. Time is not a constant. It's not the steady, cosmic metronome we perceive it to be. Instead, time is relative, and its pace is dependent on your velocity through space. Think of it as a universal speed limit. The faster you move through the 3 dimensions of space, the slower you move through the 4th dimension, time. This isn't a metaphor, it's a fundamental property of our universe, a concept known as time dilation. Imagine 2 clocks, perfectly synchronized. You keep one on Earth and you strap the other to a spaceship. As that spaceship accelerates, something bizarre begins to happen. From your perspective on Earth, the clock on the ship starts ticking slower. For the astronaut inside, everything feels perfectly normal. Their heart beats at a regular pace, they age 1 second at a time. But relative to the stationary clock back home, their personal time is stretching out, becoming languid. The effect is negligible at everyday speeds. A commercial jet flying for hours will only put its clocks out of sync with the ground by a few nanoseconds. But as you approach the speed of light, approximately 299,792 kilometers per second, the effect becomes dramatic. Let's say you built a spacecraft capable of traveling at 99.995% the speed of light. You embark on a round trip to a star system 25 light years away. For you, the journey would feel like it took about a year. You'd watch a few movies, eat some freeze-dried ice cream, and before you know it, you're back home. But upon your return, you'd find that Earth has aged 50 years. Everyone you knew would be half a century older or gone. You would have effectively leaped 49 years into the future. This isn't science fiction, it's a proven phenomenon. We see it happen with muons, unstable subatomic particles created in the upper atmosphere. They have a lifespan of just 2.2 microseconds, which should only allow them to travel about 660 meters before decaying. Yet, we detect them at ground level. Why? Because they travel at 99.9% the speed of light, their internal clocks slow down from our perspective, allowing them to survive a journey of thousands of meters. So, time travel to the future is not just possible, it's an unavoidable consequence of moving. The only catch is the engineering. The energy required to accelerate a macroscopic object to near light speed is astronomical, far beyond anything our current technology can achieve. And there's another more final limitation. This method is a one-way ticket. Special relativity offers no mechanism for going back. You can jump into the future, but you can never return to the past you left behind. It's the universe's most profound form of ghosting. Gravitational time dilation. If accelerating to near light speed sounds like too much work, there's another, more passive way to manipulate time, courtesy of Einstein's later work, general relativity. This theory expands on special relativity by revealing that it's not just velocity that can warp time, but gravity itself. Mass, according to Einstein, bends the fabric of space-time. The more massive an object, the deeper the gravitational well it creates, and the slower time flows within that well. Just as moving fast slows your personal clock, sitting deep within a powerful gravitational field does the same thing. Think of space-time as a stretched rubber sheet. A small marble, like Earth, creates a small dimple. A massive bowling ball, like a black hole, creates a deep, steep-sided funnel. Time, like a ball rolling across the sheet, slows down as it dips into these gravitational wells. This effect is happening right now, all around you. Your feet, being slightly closer to the Earth's center of mass, are aging infinitesimally slower than your head. The difference is ridiculously small, but it's measurable. In fact, the GPS system in your phone has to account for this. The satellites in orbit are in a weaker gravitational field than we are on the surface, so their clocks tick slightly faster. If engineers didn't constantly correct for this discrepancy, about 38 microseconds per day, the entire GPS network would fail within minutes, sending you into a lake when you were just trying to find the nearest coffee shop. To turn this into a practical method of time travel, you need to find an object with truly immense gravity. The undisputed champion in that category is a black hole. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. As you approach the event horizon, the point of no return, the gravitational pull becomes extreme and time dilation goes into overdrive. Imagine a brave, or foolish, astronaut, let's call him Major Tom, who decides to orbit a supermassive black hole like Sagittarius A star, the behemoth at the center of our Milky Way. From a safe distance, his crew watches him. For every hour that passes for Major Tom as he skims the edge of the event horizon, decades or even centuries could be passing for the crew on the mothership. He would be, for all intents and purposes, frozen in time from their perspective. If he were to then fire his thrusters and return to the ship, he would have aged only a few hours while his crewmates would be long gone, replaced by their distant descendants. He would have used the black hole as a natural time machine, slingshotting himself into the distant future. Like time travel via speed, this method is also a one-way trip. It's a journey forward with no possibility of return. The immense forces involved also make it spectacularly dangerous. Get too close, and the tidal forces would stretch you into a long, thin strand of human spaghetti in a process aptly named spaghettification. But the physics is sound. If you want to see the future, find a nearest cosmic heavyweight and hang out for a while.
Wormholes. Now we move from the proven and tested to the highly speculative. While Einstein's theories provide a solid foundation for one-way trips to the future, they also contain tantalizing, almost certainly impossible, loopholes that might permit travel to the past. The most famous of these is the Einstein-Rosen bridge, known more popularly as the wormhole. In theory, a wormhole is a shortcut through space-time, a tunnel connecting two distant points. It could link two places in the same universe, say your bedroom and the Andromeda Galaxy, or it could even connect two different universes. The idea arises directly from the mathematics of general relativity. If you treat space-time as a fabric, a wormhole is like pinching two distant points on a sheet of paper and punching a hole through them, creating a tunnel that's much shorter than the distance across the surface. This tunnel wouldn't just be a shortcut through space, but also through time. By traversing the wormhole, you could emerge not only at a different location, but also at a different moment. Here's how you could turn a spatial shortcut into a time machine. First, you'd need a stable, traversable wormhole. Let's assume you've solved that minor engineering hurdle. You have two mouths of the wormhole. Let's call them A and B. Initially, they are next to each other, synchronized in time. Now, you take mouth B and put it on a spaceship. You accelerate it to near light speed, take it on a long journey, and then bring it back. Due to time dilation, mouth B has aged less than mouth A. Let's say 10 years have passed for mouth A, but only 1 year has passed for mouth B. Now the two mouths are connected by a tunnel, but they exist in different time frames. Mouth B is 9 years in the past relative to mouth A. If you were to step into mouth A in the year 2050, you would emerge from mouth B in the year 2041. Step back into B, and you're back at A in 2050. You've created a gateway to a specific point in the past. The problems, however, are monumental. Firstly, general relativity predicts that wormholes, if they form at all, would be catastrophically unstable. They would snap shut in an instant, likely annihilating anything inside. To keep one open, you would need something called exotic matter, a hypothetical substance with negative mass and negative pressure. We have never observed exotic matter, and it may not even be permitted by the laws of physics. Secondly, the moment you try to use a wormhole as a time machine, you run into the thorny issue of paradoxes. What if you go back and prevent your parents from meeting? This leads many physicists to believe in something like Stephen Hawking's chronology protection conjecture, which posits that the laws of physics conspire to prevent time travel on a macroscopic scale, perhaps by causing a feedback loop of radiation that would destroy any wormhole before it could be used to violate causality. Tipler cylinders. If exotic matter isn't your style, perhaps you'd prefer to build your time machine out of something a bit more dense. In 1974, physicist Frank Tipler proposed a mind-bendingly ambitious thought experiment. He calculated that if you took a massive object, at least 10 times the mass of the Sun, and compressed it into an infinitely long, incredibly dense cylinder, you could create a time machine. The final ingredient? You'd have to spin this cylinder at a significant fraction of the speed of light. According to Tipler's calculations, this spinning, super-dense object would do something remarkable to space-time. It would twist it, dragging the fabric of space and time around with it in a phenomenon known as frame dragging. This is a real effect predicted by general relativity, albeit on a much smaller scale around objects like the Earth. But with a Tipler cylinder, the frame dragging would be so extreme that it would warp the paths of light cones, the possible future paths of any object, until they looped back on themselves. This creates something called a closed time-like curve, or CTC. A CTC is, quite literally, a path through space-time that returns to its starting point. If you were in a spaceship and you flew a precise spiral path around this spinning cylinder, you could navigate one of these CTCs. You would travel along a path that brings you back not just to your starting point in space, but also to your starting point in time. By adjusting your trajectory, you could theoretically arrive at any point in the past that occurred after the cylinder was constructed. The cylinder doesn't allow you to travel back to the time of the dinosaurs, only as far back as its own construction. The practical challenges here make building a wormhole look like a weekend DIY project. First, you need an infinitely long cylinder. Since our universe is finite, this is a bit of a non-starter. Tipler later revised his work to suggest a sufficiently long cylinder might work, but sufficiently long is still a cosmically large number. Second, the material would need to be impossibly strong to withstand the centrifugal forces of spinning at near light speed without flying apart. Third, the stability of such an object is highly questionable. Stephen Hawking argued that the laws of quantum mechanics would likely cause such a machine to self-destruct in a blast of energy before it could ever be used. Another vote for his chronology protection conjecture. So while the Tipler cylinder is a fascinating solution to the equations of general relativity, it's a time machine that will almost certainly remain firmly on the drawing board. Cosmic strings. Let's dive even deeper into the theoretical bestiary of physics. In the very first moments after the Big Bang, the universe was a chaotic soup of energy. As it expanded and cooled, it went through a series of phase transitions, similar to water freezing into ice. Some cosmological models predict that during these transitions, defects in the fabric of space-time could have formed. These aren't potholes or cracks, but one-dimensional topological defects of immense density and energy, thinner than an atom, but stretching across vast cosmic distances. They are known as cosmic strings. These are not to be confused with the strings of string theory. These are hypothetical relics of the early universe, containing immense mass. A single inch of cosmic string could weigh more than Mount Everest. Because of this mass, they would warp space-time around them. In the 1980s, physicist J. Richard Gott realized that two of these cosmic strings, moving past each other at incredibly high speeds, could create a unique and powerful space-time geometry. Imagine two of these strings flying past each other in parallel, like two impossibly fast, impossibly heavy space trains on parallel tracks. The region of space-time between them would become so warped that it would create a shortcut, a closed time-like curve. If you were to fly a spaceship in a figure-8 pattern around the two passing strings, you could arrive back at your starting point before you left. The faster the strings are moving, the further back in time you could go. This method has a certain elegance. Unlike a wormhole, it doesn't necessarily require exotic matter.
Unlike a Tipler cylinder, it doesn't require an infinite length. All you need is to find two of these hypothetical cosmic strings and hope they are moving in just the right way. Of course, the all you need part is doing a lot of work. First, we have no evidence that cosmic strings actually exist. Astronomers have searched for their gravitational lensing effects on distant galaxies, but so far have found nothing. Second, even if they do exist, the chances of finding two of them moving in a perfect parallel configuration at near light speeds are vanishingly small. Third, you'd have to somehow get your spaceship to the right place at the right time to perform the maneuver. It's a time machine built by cosmic chance, a fleeting opportunity that may never have occurred in the history of the universe. The Alcubierre drive. What if, instead of moving through space, you could move space itself? This is the radical idea behind the Alcubierre drive, a theoretical concept proposed by physicist Miguel Alcubierre in 1994. It's a form of warp drive that allows for faster-than-light travel without technically breaking the laws of relativity. Einstein's theory states that nothing can move through space faster than light, but it places no limit on how fast space itself can expand or contract. After all, the universe expanded much faster than light during the inflationary period just after the Big Bang. The Alcubierre drive works by creating a warp bubble of space-time around a spaceship. In front of the ship, space-time would be contracted. Behind the ship, space-time would be expanded. The ship itself would remain stationary inside this bubble, like a surfer on a wave. The wave of space-time would be the thing that's moving, carrying the ship along with it at potentially enormous speeds, far exceeding the speed of light. How does this relate to time travel? Any form of faster-than-light travel is, in effect, a form of time travel. Imagine a star 100 light-years away. If you could travel there in 1 year using an Alcubierre drive, you would arrive 99 years before the light from your departure point. You would be able to see Earth as it was when you were just leaving. You have effectively traveled into the past of that distant location. By setting up a chain of FTL jumps, you could construct a path that leads you back to your starting point in space, but at an earlier time. You would have once again created a closed time-like curve. The Alcubierre drive, however, comes with a shopping list of seemingly impossible requirements. Like the wormhole, it requires vast amounts of exotic matter with negative energy density to create the warp bubble. The amount needed was initially thought to be more than the mass of the entire observable universe, though later refinements have brought that down to a more modest planet-sized mass. Furthermore, there are other nasty side effects. The front of the warp bubble would accumulate high-energy particles, which would be released in a deadly blast of radiation upon arrival, vaporizing your destination. Also, the crew inside the bubble would be causally disconnected from the outside, meaning they couldn't steer the ship or decide when to stop. It's a time machine with no brakes and a very messy arrival. Quantum tunneling. Moving from the cosmic scale to the subatomic, we enter the bizarre and counterintuitive world of quantum mechanics. Here, particles don't behave like tiny billiard balls, but like waves of probability. One of the weirdest quantum phenomena is tunneling. Imagine throwing a ball at a wall. In the classical world, if the ball doesn't have enough energy to go over the wall, it will never get to the other side. But in the quantum world, there is a small but non-zero probability that the ball can simply appear on the other side of the wall without ever having had the energy to pass through it. This is quantum tunneling. It happens all the time. It's the reason the sun shines, as it allows protons to fuse together even when they don't have enough energy to overcome their mutual repulsion. Could we use this for time travel? Some physicists like Yakir Aharonov and Lev Weidman have explored the idea that quantum tunneling might not just be a passage through a spatial barrier, but also a temporal one. In some interpretations, a particle that tunnels could be seen as taking a shortcut through space-time, effectively traveling faster than light for a brief moment. This superluminal travel, as we've seen, opens the door to time travel paradoxes. More advanced theories speculate about tunneling through the space-time metric. In essence, it might be possible for a particle or even a macroscopic object to tunnel from one point in space-time to another, including a point in its own past. This would be like finding a quantum wormhole, a probabilistic shortcut that bypasses the normal flow of causality. This is by far the most speculative and least understood method on our list. The mathematics is fiendishly complex, and it's unclear if these ideas are just mathematical artifacts or descriptions of a real physical possibility. The probability of a single atom tunneling is already low. The probability of trillions upon trillions of atoms that make up a human being all tunneling to the same point in the past in a coherent way is so close to zero as to be functionally impossible. It's a time machine that relies on winning the lottery with odds that make winning every lottery on Earth simultaneously look like a sure pat. Closed time-light curves. Many of the methods we've discussed, Tipler cylinders, cosmic strings, FTL travel, are really just different ways of achieving the same theoretical goal, the creation of a closed time-light curve, or CTC. A CTC is any path in space-time that an object or person can take that ends up in its own past. The concept was first mathematically identified by Kurt Gödel in 1949, who found a solution to Einstein's field equations that described a universe filled with a rotating fluid. In Gödel's universe, the rotation is so extreme that it drags light cones over, allowing for paths that loop back in time. The existence of CTCs in a physical theory is deeply troubling to most physicists because it implies that causality can be violated. This leads to the infamous grandfather paradox. What happens if you go back in time and prevent your grandfather from meeting your grandmother? If you succeed, you were never born. But if you're never born, you couldn't have gone back in time to do the deed. It's a logical contradiction. Physicists have proposed a few ways to resolve these paradoxes should CTCs prove to be real. One is the Novikov self-consistency principle. This principle states that any event that occurs on a CTC must be self-consistent. The laws of physics will conspire to make paradoxes impossible. If you went back to stop your grandfather, you would find that you failed, no matter what you do. Your gun would jam, you'd slip on a banana peel, or you'd discover that the man you thought was your grandfather was actually someone else. The universe would enforce a single consistent history. In this view, you can participate in the past, but you cannot change it. You would simply be fulfilling a role that was already part of history. Another possibility comes from the many worlds interpretation of quantum mechanics. In this view, every quantum measurement causes the universe to split into multiple parallel universes, one for each possible outcome. If you travel back in time, you don't enter your own past, but the past of a parallel universe. You could prevent your grandfather from meeting your grandmother in that universe, but it would have no effect on your own history because you originated from a different branch of reality. This neatly resolves the paradox, but at the cost of creating an infinite number of parallel timelines every time a time traveler meddles with the past. The grandfather paradox. The grandfather paradox is the poster child for the problems with time travel. It represents a whole class of paradoxes that arise from the idea of changing the past. But it's not the only one. There's also the bootstrap paradox, which deals with information or objects that have no origin. Imagine a time traveler gets a copy of Hamlet from the future, travels back to Elizabethan England, and gives it to Shakespeare, who then publishes it as his own work. The question is, who wrote Hamlet? The information exists in a closed loop with no point of creation. These paradoxes are so profound that they have led many to believe that travel to the past is simply impossible. But the self-consistency principle and the many worlds interpretation offer potential, if mind-bending, ways out. Let's revisit the Novikov principle. It suggests that free will, in the context of time travel, is an illusion. You might feel like you are making choices, but the outcome is predetermined. If you travel to the past with the intention of changing it, you will find that your actions were, in fact, the very things that caused the history you know to happen. Your attempt to prevent a fire, for example, might be the act that knocks over the lantern that starts it. You are not an agent of change, but a cog in a fixed, immutable machine of space-time. The many-world solution is, in some ways, more liberating. It preserves free will. You can go back and do whatever you want, creating new timelines with every action. But it also raises profound philosophical questions. If you save someone's life in a parallel past, have you done a good deed? What about the universe you left behind? Is it possible to get back to your original timeline? This version of time travel isn't about changing history, but about escaping it, becoming a refugee in a different stream of time. It resolves the paradoxes, but it makes the past a messy branching tree of infinite possibilities, a far cry from the single linear history we experience. The Novikov self-consistency principle. Let's end by digging a little deeper into the most elegant and perhaps most unsettling solution to the time travel paradoxes, the Novikov self-consistency principle. Proposed by Russian physicist Igor Dmitrievich Novikov in the 1980s, it's a simple but powerful idea. The principle states that the probability of any event that would lead to a paradox is zero. Simply put, you can't create a situation that is not self-consistent. Imagine a billiard ball rolling towards a wormhole that will send it 1 minute into the past. It emerges from the past mouth of the wormhole on a collision course with its younger self. If it hits its younger self, it will knock it off course, preventing it from ever entering the wormhole in the first place. This is a paradox. Novikov's principle says this outcome is impossible. What would happen instead? Physicists Kip Thorne and his students at Caltech ran computer simulations to find out. They found that for a wide range of initial trajectories, there was always a self-consistent solution. The billiard ball would emerge from the past and deliver a glancing blow to its younger self, a blow that was just enough to alter its path so that it would travel through the wormhole and emerge to deliver that very same glancing blow. The history is consistent. The event happens because it happened. There is only one timeline, and it is unchangeable. This principle implies a deep and mysterious property of the universe, that it is fundamentally logical and will not allow contradictions. If time travel to the past is possible, it must operate under this rigid constraint. You could travel to the past, but you would be a historical actor, not a historical editor. You could witness the signing of the Declaration of Independence, but you couldn't add your own name to the bottom. You could meet your younger self, but any information you gave them was information they were already destined to receive. This is the ultimate cosmic straitjacket. It allows for the possibility of time travel while stripping it of its most dramatic and dangerous potential. You can visit the past, but you are a ghost there, your actions already woven into the tapestry of what has been. It suggests a block universe, a four-dimensional reality where past, present, and future all exist simultaneously and are equally real. Time travel, in this view, is not a journey of change, but merely a journey of perception, a different way of reading a book that has already been written.